He has more than 23 publications in various national and international journals and symposiums. He is also a peer reviewer of various technical papers for various international journals like ASCE's International Geomechanics and Journal of Geotechnical and Geoenvironmental Engineering, to name a few. Thank you. Mr. Pratik, please continue.
Thank you, sir, for such a wonderful introduction. Now I will request Mahendra Singh, sir, to introduce, to welcome our esteemed speaker. Singh, sir, please.
Thank you, Pratik. Pratik, am I audible?
Yes, sir, you are audible.
So at the outset, many thanks, Dr. Birid, for sparing your time and giving this wonderful lecture. It's a very, very important chapter. And on behalf of the IGS Roorkee, it's my pleasure to welcome all the attendees, and I hope this lecture will be very, very fruitful. With this, I once again welcome you, and please proceed further.
Thank you, sir. Now I request Professor N.K. Samadia, sir, to say a few words for the lecture and the speaker.
I would like to thank again Dr. Birid for accepting our invitation. And on behalf of Department of Civil Engineering, IIT Roorkee, we welcome you, and we are eager to listen to the lecture. As Professor Mahendra Singh has said, that it is a very important lecture in the sense that it is from an expert who is working in field. Most of the lectures normally are given by academicians, and mostly the theoretical or research. So thank you so much. And
I can see more than around 77 participants are there. So that speaks of the popularity of this particular topic. Welcome.
Okay, before that, I would like to just inform all the participants, if you are IGS member and you have become member before 31st of March 2024. So IGS elections are on, nomination process is going on. If you are interested to become executive committee member, you can submit your nomination by 30th of August. And there is one mock voting process is also going on. So I would like to request all of you to validate your credentials and participate in this mock election. Actual election will start in September. But since we are going for online and we have changed the procedure, so that's why it will be easy for you if you have gone through the mock test, and you will not feel any difficulty in actual voting process. So I invite you, please participate in the mock test in large number. Thank you.
Thank you, sir. Now I request Dr. Kedar Birid, sir, to start the lecture. Sir, the dice is yours. Thank you.
Thank you, Professor Mahendra Singh, Professor Samadia, and Dr. Kaustav for the brief introduction. So I'll just straight away start with my presentation. Kindly let me know once my screen is visible to all.
No, sir.
It's coming on. Presentation is not coming.
Not there?
No, sir, it's not visible. I think.
I'll try to reshare.
I think you can disconnect and reshare again, sir.
Okay. Is it visible?
Yeah, it's now.
Yes, it is coming.
It's visible.
It is coming. Yeah.
Okay. So basically my presentation is about the forensic geotechnical engineering or the geotechnical forensic engineering. So it's as said by Professor Samadia, I will not go much theoretical about it, but it's basically about the case studies, what I came under the supervision or under the consideration during my tenure working with the industries. The case studies are mainly related to the failures. The failures mainly because of the kind of human errors to some extent. Some failures are because of the unpredictable geological features or the unpredictable topographical features. I'll just explain what kind of failures were there. Then I'll also explain how we identified the root causes of that each and every failure and what kind of rectifications measures that we adopted so that such kind of failures will not happen again in future. So basically I will cover the 5 different case studies from different regions in India and abroad. So first case study is related to the underground pit failure. The second study is related to the failure of raw water reservoir. It's basically the slope failure. The third case study is related to the uplifting of the intake structure. Again, it is an underground structure for the industrial plants. The fourth case study is about the settlement of the foundation, a typical case study which we come across on many projects. And the last case study is related to the corrosion of steel pipes, which mainly support the tank structure, the overhead tank structures. So just to start with the first case study, which is related to the underground pit failure. So what you can see in the screen is the underground pit, which is partially completed. This pit is, as you can see, it was 90 meter in length and the 45 meter in the width. The depth of this particular pit was 10 meter. The purpose of this pit was to collect the contaminated water from the industrial plant and then treat this particular water before discharging it into the discharge system, into the outfall system. So the pit was under construction. This is particular location is particularly in the Mangalore region in Karnataka. The pit was under construction. It was partially completed. The side wall of the pits were completed. The thickness of this side wall was almost 0.8 meter, 800 mm. And this pit was divided into 2 partitions by a partition wall, again 10 meter high and 0.8 meter thick. The bottom of this particular pit was constructed using the raft foundation with almost 1 meter of thickness of the raft. The pit was under construction and during the rainy season, there was some problem. Again, you can see in this previous photo where you can see some crack in the partition walls of this particular pit. This is the close-up view of that particular damage where there was a crack developed in the partition wall of this particular pit. Just note down that the thickness of this wall was 0.8 meter. This is the photograph taken from the top of the wall where you can see through and through. You can see the rebars reinforcement, which is clearly sheared off with typical cup and cone failure, what we generally observe when we do the testing of the tensile testing of the rebars in the UTM, in the laboratory. So that kind of typical failure was observed. Again, some beams and columns were in place in the other half. So we could see some cracks develop on that particular beams as well. This is the scenario of the foundation bottom. That is the raft of that particular pit. So this was the 1 meter thick raft, and you can clearly see the damages happen to the raft. It basically got uplifted, and even the rebars inside those bars got bent because of the uplifting. Again, few cracks which were observed at the bottom of the foundation, on the raft foundation of that particular pit. So we tried to analyze the cause of the failure. So first of all, we tried analyzing the topography of that particular location where the pit was located. Based on this cross section, vertical cross section, what you can see on this top picture, what we observed that there was a bedrock profile, which is having the slope from the west direction towards the east direction. It is almost dipping down by say 8 meters from the west towards the east. And this is the location of that particular pit where it was resting. There was a soil, the filled up soil above this particular bedrock profile, as you can see over here. And this is the natural soil below the filled up soil up to the bottom of the bedrock. There were some wells, existing wells like this, located at that particular site next to the pit. And we could observe some higher rise in the water level in such wells. Immediately, we installed some steel tubes in the ground, and what we could observe that the water is coming out from that particular tubes, which from the holes in that particular tubes, and with the level you can see, which is very well above the ground level. So prima facie, this was a clear indication that there was a rise in water table, which was almost above the ground level, above the existing ground level, which is mentioned as the finished ground level. Later, we tried to analyze some topographic feature. So this particular image shows the location of that entire plant where that pit is particularly located. So here, this location of the particular pit, you can see entire greenery. On the west side of this particular location, particular site, there was a hill which was almost 40 or 50 meter high with respect to the level of this particular plant location. As this was the monsoon season, there was a heavy rain, and we could also observe some accumulation of the water on the top of the hill. So this is the location of that particular pit, underground pit. One thing would again like to highlight over here that earlier, before the construction of this particular industrial plant, this used to be a village, a small village. And in this particular village, there used to be a well, a kuwa, with perennial water in that particular kuwa. The slab which you see over here was constructed to close that particular well to take care of the construction of this industrial plant. So this well which was earlier there was closed by constructing this slab on the top of it. So when we did the investigation earlier, before starting the construction and before the engineering of this particular project, we observed the groundwater table, which was 4.3 meter below the existing ground level. While designing the particular underground structures or the foundations, conservatively we consider the water table at 3.3 meters, considering the probable rise in water table by 1 meter, maybe due to the monsoon or due to some other reasons. However, the actual water table, what we observed at site during the failure, during the monsoon, was almost 0 meter. So the actual water table has been increased up to the ground level due to the topographic feature, the high ground at the west side of the particular industrial plant, the geological feature, where you can see the bedrock which was sloping away from the pit at the west side, and it was sloping down towards the pit. So it was the reason for carrying the groundwater flow from the high levels to the low level where the pit was located. Because of this increase in water table up to the EGL existing ground level, the factor of safety against uplift was reduced to 0.7, which is less than 1, and which causes the uplifting of the pit because of the buoyancy. So this was the root cause for that particular uplifting and particular damage to that pit. So all these problems together, such as topographic feature, the rise in water table because of the monsoon, the closure of the existing well, which prevented the release of the pore water pressure, and the accumulation of water body at the high level on the hill, which created the hydraulic gradient from higher level to the lower level towards the location of that particular pit. All these features together caused the problem, because of which the pit got uplifted and got cracked. Once the root cause was clear, we visited the site immediately. As the pit size was very huge, 90 meters by 40 meters in plan dimension, it was very difficult to perform any immediate rectification measure, permanent kind of rectification measure. However, the monsoon season was ongoing, and we observed that the pit was uplifting day by day, almost by few centimeters. So there was a requirement for some immediate rectification measure to stop the uplifting of that pit. So what we decided that let us divert the water which was accumulated around the pit because of the rain. We diverted that particular water inside the pit. So this created the dead weight inside the pit and help us in stopping the uplifting of the pit. And after a few days, when the pit was filled with the water almost completely, it settled back to its original position. We further engaged agencies such as IIT Madras to carry out the detailed analysis, the field testing at site to check what are the distresses that have happened to the pit, to the concrete structure, as well as to the subsoil which is present below the pit. So IIT Madras carried out some detailed study, detailed field investigation using the GPR, ground penetrating radars, some seismic study to check the velocities or the indirect densities of the subsoil near or below the location of the pit. Some undisturbed samples were collected to check the properties of the soil. Few infiltration tests were also carried out. The specific body like the boat kind of structure was prepared, developed by IIT, so that the GPR machine can be installed inside that particular floating body, so that the pit, which was already filled up with water, can be surveyed using the ground penetrating radar. So such kind of floating body was prepared, and the GPR was placed inside and towed all along the length and width of the pit, just to map the subsoil conditions at the bottom of the pit. The outcome of the survey reveals some voids, some channels, some tunnels, maybe because of the piping kind of phenomena where the soil has flown because of the flow of the water from east side towards the west. So these are some locations where the voids have been detected, which indicated some erosion of soil below the bottom of the tank. So this is the bottom of the tank. Again, some reduction in the density of the subsoil was observed, maybe because of the underground flow of the water during the monsoon. So we had to decide the permanent rectification measures so that such phenomena should not happen again. The pit was already under construction. It was already partially completed. So it was not possible to alter its design and reconstruct the pit by demolishing the existing pit. It was not possible. So we had to think about some other alternatives. The first option, what we thought, was installation of trench drain and the sump pit like this along the periphery of pit. The trench drain would act as a drainage system, such as stormwater drains, and the sump pit would act as a dewatering system, so that whatever water is collected in the trench drain could be dewatered from the sump pit. And in that way, we could lower the groundwater table. Another option was the installation of relief wells, maybe up to 10 or 20-meter depths. So it's just like a boreholes along the periphery of the pit, and filling these particular boreholes with perforated pipes, and the dewatering of the water from this particular borehole. So again, to lower the groundwater table whenever there is a rise in the water table around the pit. Another option was the installation of relief wells, not along the periphery, but directly inside the pit, so that the whatever excess pore water pressure is getting generated below this bottom of the pit could be released through these relief valves inside the pit. Another option was again the provision of dead weight by virtue of putting some concrete, some PCC. However, again, this was rejected by the operations because this would reduce the capacity of the pit, what it was actually designed for. And the last option was the provision of ground anchors, which would probably anchor and hold this pit right in the bedrock, so that it will prevent the uplifting of this particular pit, even though there is a excess pour water or the rise in the hydrostatic pressure. However, again, this option was one of the costliest option among all. And ultimately, as we always know, in an Indian scenario, the client or the contractor always try to save the cost due to many project-related constraints. So this, being one of the costliest option, was ultimately rejected by the client. So finally, we went ahead with option 2 of the provision of relief well all along the periphery of the pit. So this is the layout of that particular pit, and the green square, what you can see, is the location where we have installed the relief wells. So relief wells was nothing but a borehole of 20-meter deep, and we installed the perforated pipe inside this borehole. We put the pump assembly at the bottom of this particular borehole with the actuator. So actuator is the automatic system which performs the dewatering once the water level reaches to particular height inside this borehole. So when the water level reaches, for example, 5 or 6 meters, the pump will start automatically, and they will start dewatering and putting the water, diverting the water in the other stormwater drainages nearby. So such kind of system was installed all along the periphery of the pit. This was a permanent rectification measure. It was required to be operated throughout the life of the plant. This is the photo of the dewatering well, the borehole, the perforated pipe inside this particular borehole. And you can see the space between the borehole wall and the perforated pipe was filled with the granular material, which is highly permeable in nature, so that it is easy for water to get accumulated in this particular standpipe, and it can be dewatered easily using the pumps. The voids which were observed during the GPR survey in the subsoil below the bottom of the pit were later grouted by using the cement grout. So inside the raft foundation, some holes were drilled so that the grouting can be performed using the cement epoxy grout. So in a grid manner, the grouting was done, and that way the bottom raft foundation which was damaged was rectified using the high strength epoxy grout. The details were published in a journal, so maybe all other technical details, which I'm not going now in detail, can be referred in this particular paper. So coming to the next case study, which is again from the same region, Mangalore, where you can see this is the raw water reservoir. So it is a reservoir to collect the raw water. And one fine day, we observed that the failure of some of the panels took place, and it is a typical kind of slope failure. Again, the depth of this particular reservoir was 7 meters, and the slopes were, I think, 1:2.5. Again, the detailed study was performed inside as well as the outside of this particular reservoir using GPR, ground penetrating radar, by IIT Madras. Again, the survey was done, the scanning was done inside the water body, inside the reservoir. You can see it over here. The outcome revealed some loose pockets along the slope, which was already filled. So you can see over here some loose pockets were observed, which was probably again due to the underground flow of water from high grounds towards this particular reservoir. And because of that, the additional hydrostatic pressure was imposed on the slope of this particular wall of the reservoir, causing its failure. Some fractures, voids were also detected where the slope was particularly failed. So there was no temporary rectification for this particular problem. So we had to do some permanent rectification measures. So we prepared a scheme to reconstruct the damaged slope with the provision of grids of the beams, horizontal and the vertical beams. And additionally, we provided the pressure relief wells all along the newly constructed concrete slope. So this is the section of the particular relief well, which was again constructed on the slope. The periphery filled with the highly permeable material such as gravel, so that in case there is again the flow of water or the generation of excess pore water pressure, it could be released through this relief well. So the entire filled slope surface was removed. It was destroyed completely. We refilled the damaged soil, the soil which was eroded because of the underground water flow. We refilled the slope using the good soil, and the entire paneling, the concrete paneling was reconstructed. You can see these particular slabs over here where we constructed additional relief wells so that this pore pressure can be released through this particular points in case of any additional hydrostatic pressure in future. So again, we presented one paper with this particular case study in the international symposium. Coming to the third case study, a very important case study, again, the uplifting of the seawater intake structure. So this is the model of that particular, again, underground structure. The length of this particular structure is 46 meters, the width is 33 meters, and the depth is 15 meters. The important aspect of this particular structure is the location. This was located in the state of Gujarat, in the Mundra region, and it was just next to the seashore. So you can see this location of this particular underground pit. This entire land was reclaimed by Adani, and the reclamation was up to 5 meters inside this sea. And we were given this land to construct this LNG terminal, and the underground seawater intake structure was part of this particular project. And the location you can see just next to the seashore, which was already on a reclaimed land. The reclamation was 5 meters, and the depth of seawater was almost 10 meters at this particular location. The reclamation again was done using the highly permeable soil, such as sandy soil. So it was challenging for us to construct this underground pit in a highly permeable material such as sand, because we had to do the excavation up to the 15 meter, which was almost 10 meter below the seawater surface. So this is the photograph where we started doing the construction of this particular pit. The side walls of this pit were constructed using the diaphragm wall technique. And once the diaphragm walls were constructed, they were in place. We started excavating inside this particular pit to reach up to the bottom of the founding level. Once we reached this founding level, we were about to start the construction of the foundations. So the side walls were constructed first using diaphragm wall techniques, and the foundations was later constructed. You can see this arrangement for the bonding or the bonding of the foundation of reinforcement in the diaphragm wall system. So as we started the construction, diaphragm walls was complete. We started the excavation up to the 15 meter depth. When we reached almost 15 meter and laid the PCC, before laying the actual RCC foundations, we noticed some cracks in the PCC. We also noticed some sand boiling, okay, where the water, we could see the water which is literally coming out as a boiling water from the bottom of the pit at many of the locations. We could also observe some differential settlements in the diaphragm wall. So this is the diaphragm wall, two different panels, the left side and the right side. And we could see the differential settlement, and because of which we could see the crack in between the cold joint of the diaphragm. Further, you can see over here, we put a glass plate to monitor if there is any further settlement happening. if there is any further settlement, this glass would crack. So that would indicate that yes, it is still settling differentially. At the top of this particular pit, there was a support system, there were struts, and we could see some cracks at the joint of the struts whenever it is getting joined to the diaphragm wall, wherever it was connected to the diaphragm wall. So some cracks were observed. So again, it is indicating there is some movement of the diaphragm wall with respect to the movement of these struts. So before construction of this particular pit and before starting the excavation, we had already provided the well point system. So well point system is typically a dewatering arrangement along the periphery of any excavation. This is just an example where we put a series of vertical wells and they are connected with a common header, and the dewatering is carried out simultaneously through all the wells so that the groundwater table can be lowered below the excavation level. So this is a typical arrangement which was already in place. So this is the layout of the pit, and you can see those points 1 to 39, which are the location of the well points. So you can see there were number of almost 30 sufficient number of well points which were in place with a pump inside for the 24/7 dewatering during the excavation of this particular pit. The typical soil profile, as I said earlier, it was a reclaimed land. So majority of the soil was consisted of medium dense to dense sand with the presence of some silt from the 0 to 12 meter depth. There was a thin layer of very soft sandy silty clay, a thin layer of impermeable soil. Again, there was a layer of dense silty sand with some clays. And again, there was a medium dense to dense layer of sand. So entire profile from top to bottom, where the diaphragm was constructed, consisted of the highly permeable soil of sand. This is the length of the diaphragm wall, which was well below the bottom of the excavation, almost up to 23 meters from the top, because the excavation was required up to the 15 meter. This was the length of the well points, which was outside the pit, which was almost beyond the depth of the diaphragm wall, maybe from minus 15 to 8.5. So it was almost 23 meters deep. So we decided to carry out some studies, some numerical modeling, numerical analysis using the MATCAD script. And what we could observe is basically the difference in hydraulic gradient between the outside and inside pit, which was again obvious because we were doing the dewatering inside the pit to facilitate the construction of the raft. The uplifting and the cracking of CC was mainly because of the upward water pressure inside the pit. We could clearly observe the flow of water from outside inside of the pit. The soil erosion also took place because of this flow, and there was a piping failure and the settlement of this particular diaphragm wall. So this is the diaphragm wall model in the numerical analysis. And because of this underground flow, the diaphragm wall, there was some erosion of the soil beneath the diaphragm wall bottom, and subsequently there was a settlement of this diaphragm wall, which was differential in nature. Soil erosion, again, due to the water flow below the diaphragm wall, and the factor of safety for the piping failure was observed as 0.78, which was less than 1. And because of that, ultimately there was a series of failures, such as crack between the diaphragm wall panels, the cracks between the struts and the diaphragm wall. So it is sequence or the series of events that took place because of this flow of water. So as a rectification measures, we had to increase the flow path of the water from outside to inside. That was the first thing what we wanted to do. So we thought of increasing the flow path by doing some grout injection below the diaphragm wall so that the length of the flow path could increase. Another option was to install the additional row of dewatering wells, again some distance outside the existing row of water, so that the additional pumping could be done. And again, because of that, the flow path could increase, and which could obviously could reduce the ingress of water inside the excavated pit. So we also involved Professor Dipankar Chaudhary from IIT Bombay to help us in rectifying this particular problem. So as you can see over here, this is the particular well point originally placed in position. This is the pit, and here is the additional row of well point what we installed as suggested by Professor Chaudhary. And we almost increased the number of additional wells by 20 with additional pumps in those particular width with a higher capacity. This could rectify the problems. We could do the safe excavation inside the pit. There wasn't any additional ingress of the water after the installation of additional well points outside the pit. Just to make a little bit more safe, we also installed the pipes like this. These are called the vent pipes, penetrating the foundation right in the subsoil, so that if at all there is excess pore water pressure, it could be released to this particular vent points. After the construction of raft foundation, these vent pipes were sealed using the cement grout. So we could rectify this particular problem by the additional well point systems. The next case study is about the settlement of the problem foundations, typical problem which generally we encounter at most of the sites. The main reasons for such settlements are the improper design of the foundations, improper revelation of the SBCs, or the improper compaction of the subsoil on which these particular foundations are resting. So this particular case study is mainly human error related. This is again from one of the projects in Egypt. So this particular industrial project was again for the regasification plant in Egypt. This particular site was filled. This particular site was raised using soil, externally filled soil, almost up to 2 meters. During the filling of the soil, the precautions were taken to lay the soil in proper layer-wise manner or with a proper compaction with all the records in place. These are the foundations on which the pumps are going to be rested. So these are the small pump foundations. And you can see these foundations got settled to some extent. Few foundations got tilted. So you can see the thickness of the foundations, which is a little bit less over here, which is a little bit more over here. So it has got tilted on this particular direction. The foundation, surprisingly, the foundation got tilted without any pumps or without any additional load on top of it. The attempt was made to lift these foundations. Obviously, the root cause of this particular problem was improper compaction of the subsoil or the presence of loose soil beneath the foundation, even though all the records, proper records with a proper compaction were in place. But the root cause was the improper compaction, and we had to do the improvement of the subsoil, which was loose in nature. Our first attempt was to lift this particular foundation because the foundation was very small in size. The weight was around 8 tons per foundations. So we lifted these foundations using the crane, and we placed these foundations aside. We compacted this subsoil with a proper good soil with proper compaction, and we again replaced this foundation on the compacted soil. However, such affected foundations were almost 50 in numbers, and it proved quite impractical due to the space constraint. You can see very tight space over here to operate the crane, very less headroom because of the construction was almost completed for the pipe rack structure. And it was not possible to do this exercise for each and every foundation. It was a huge time consuming as well as cost consuming. So we had to think about some other alternatives. So we decided not to disturb the foundations which were already settled and tilted, but we decided to do some kind of strengthening below these foundations. The type of soil on which these foundations were resting was mainly silty, fine sand with majority of silt. We studied different options of the grouting below these particular foundations using the different materials such as cement, Portland cement, with the cement mixed with the bentonite, the microfine cement, the silicates, the colloidal silica, which are type of chemical grouting, as well as the resin, which are again the specialized type of chemicals for the grouting. You can see from this particular chart that each type of grouting material has applications in the different type of soil. Based on the soil which we were having at our project site, we thought the colloidal silica was the correct material which can be used for grouting beneath the foundation bottom. We prepared a scheme to inject this colloidal silica chemical grout. It's a liquid form, using the inclined grout pipes, which would go beneath the foundation bottom and which would inject the grout and increase the strength of the subsoil. So this is, you can see the equipment where we positioned it in an inclined manner, almost 30 degrees to the vertical, and we tried to do the inclined borehole. And you can see this PVC perforated pipe is inserted in an inclined manner. This is just a trial location. We did few trials by doing the exercise with injecting grout in a different grout holes with a different grout pressure. With a zero grout pressure, the grout pressure we increase up to the 50 kPa during the different trials. And we collected the samples before grouting and after the grouting from the different pits. What we could see from this particular charts that we observed some decrease in void ratio from ungrouted to the grouted soil samples, some decrease in the compression index from ungrouted to grouted soil samples, and again some increase in the cohesion of that particular silty soil in the last trial, which is very good from the grouted samples. So based on these trials, we finally decided to go ahead with this solution. So accordingly, all the foundations, all the affected foundations were grouted by using this inclined grout pipe, as you can see in this particular photograph. As one of the other exercise as a trial, we also loaded the foundations using the load, which is equivalent to the 4 times of the weight of pump, which is going to come on the top of it. So first we did the grouting of this particular foundation. Then we sealed this particular area by inserting the bentonite grout, what you can see this pipe. And then we flooded this particular area to simulate the monsoon condition. If at all there is a rain and if these sites get flooded again, so what could be the behavior of the grouted soil. So we did a continuous flooding, we put additional load, and then we measured the settlement of this particular foundation initially for 7 days and then continued for almost for 3 months. And we could hardly notice the settlement of 3 mm or 4 mm after the grouting, which ultimately proved that our scheme was successful. And coming to the last scheme of the case studies, this is for the particular related to the tanks, the storage tank, which is basically for the storage of liquid ammonia. This is the typical liquid ammonia storage tanks. The specific thing about this particular tank is the air gap, what you can see over here. So ammonia storage tanks always has a 1 meter of air gap between the ground level and the bottom of tank. This is required from some operational point of view to keep the bottom of the tank in a cool condition. So this is a typical ammonia storage tanks. This case study is from Nigeria, where we had a 60-meter diameter of similar ammonia storage tanks. This is the actual photo of the tank with the air gap, you can see. And you can see the pile foundations which were supporting this particular tank. So this was a pile raft kind of foundations, piles throughout the bottom raft of the tank. These are the steel piles, hollow steel piles. You can see the another photo of this particular tank and the steel pipes, which can be seen, which are only along the outside, but you cannot see in the piles which are inside. So this entire tank is filled with the pile foundations. What we observed immediately after the 3 months after the construction of this particular tank, the steel piles started corroding. So there is a continuous corrosion of the steel piles, which started immediately, almost after the 3 months of the construction of this particular tank. The plant life is 30 years generally. So everyone was worried that it has started corroding in 3 months. So what would happen in 30 years? The tank was already in place. The piles are already in place. We cannot do any destructions. We cannot destroy this structure and construct the new tanks. We cannot go inside and do some painting or some kind of anti-corrosive treatment to the steel piles. It is a 60-meter tank. It is practically impossible to do that. So we had to think about some other solutions than doing some rectification in the field. So this is a particular case study where we try to qualify the safety of this particular tank and the steel piles based on some analytical solution or based on some calculations. So the diameter of this particular steel piece was 508 mm. The thickness of the steel pile was 12 mm. And as I said, the plant life for that particular project was 30 years. There is a European code available for the estimation of the corrosion rate of the steel, where they have given the atmospheric corrosion rate as 0.02 millimeter per year, typically for the steel, the grade of the steel that we used for this particular project. So there would be a reduction in the thickness of 0.6 mm over the period of 30 years, considering 0.02 mm per year. So if at all we consider the tank, the steel piles would also corrode from inside, the reduction in thickness would be double. So it would be 1.2 mm in 30 years. So our thickness of the pile wall will reduce from 12 mm to 0.8 mm. Fine, we got the reduced thickness, what it would be after the 30 years. So we tried to analyze the load carrying capacity of the steel piles with the reduced thickness. So we generated this curve where you can see the unfactored axial load on the y-axis and the unfactored bending moment on the x-axis. This is the typical curve what we generally get for the pile foundations, whether it is a concrete pile or steel pile. This is the curve what we have got for the steel pile with 12 mm thickness, and this is the curve with the reduced axial load and the reduced bending moment for the 10.8 mm reduced thickness of the pile. What actual load is coming on the pile? This is the actual load that is coming on the each pile based on the load of the superstructure, based on the seismic load, based on the wind load, etc. So actual load is well within the capacity, unfactored capacity of the steel pile even after the reduced thickness. So we were still safe because the load was quite less than the reduced capacity of the pile because of the reduced thickness. So that is how we tried to qualify this particular problem without doing any rectifications in the field. So this was the last case study. So what ultimately I would like to emphasize that we as a geotechnical engineer face different challenges, different projects. There are no typical challenges for all the projects. They always vary. Each problem can have a multiple solutions. Like the case study I mentioned about the uplifting of the underground pit. So we had a multiple options, multiple solutions, and we had to choose the optimum and the best solution out of that. And obviously, as a geotechnical engineer, we are also required to think out of box, which I explained in the case study, where we had to study the topographical features, the geological features, not just concentrating in and around the pit where the damage was observed. So we do have to think out of box, and little bit innovative. So thank you very much for your kind attention. Till I think 10 minutes left. If you have any questions.
Thank you, sir. That was a very nice lecture. We have some questions. There is one question from Sandeep. How was GPR used in the wet environment?
In a wet environment, the GPR study is generally carried out on the surface. So what you can see from the photograph there were, I'll just come to there. So the surface has to be relatively dry. It was not the complete wet surface. You can see there was an existing road over here on the top of the reservoir along the periphery. So the GPR was performed on that particular road. You can see this particular soil, which was not totally completely wet. So we could perform the GPR conveniently, safely.
I think that must have answered the question. The second question is, were the reasons for corrosion of steel pile evaluated?
The reasons for the corrosion of steel piles were environmental, mostly. And it was to some extent, it was also related to the corrosive nature of the subsoil in that particular region. It was in Nigeria, which was not probably studied properly beforehand. So that was the main reason. It was environmental as well as the subsoil related.
So the next question is, how the corrections to the factor of safety calculated?
The corrections to the factor of safety?
Calculated.
Okay. Regarding the uplift of the factor of safety was less, 0.7, because of the rise in groundwater table. So the factor of safety got ultimately increased once we installed the relief wells all along the periphery, and once the groundwater was lowered. So automatically the factor of safety got increased against the buoyancy.
Okay, I think that has answered this question. So the last question is, in the first case, there were air pockets. So how these air pockets were rectified in the first case study, sir?
They were rectified by using the grouting. As I mentioned, we did some grouting from the bottom of the pit. We did some holes in the foundation raft, went through. Then some grout nipples were installed, and we tried to grout it using the high pressure grout, epoxy grout. We don't know, to be honest, we don't know whether all the detected pockets were completely filled or not. But to be honest, it's quite difficult to assess that post rectification. But based on the manner in which we did the grouting in a grid pattern all over the entire area of the bottom raft, we assume that it could have resolved the voids. It could have filled the voids with the grout.
Okay, sir. That was a nice session, and I think most of the questions have also been answered. Now I request Professor N.K. Samadia, sir, to present the vote of thanks. I think Samadia, sir, is not here. Then I request our President Sushant Rahul, sir, to present the vote of thanks.
Thank you, Pradeep. I would like to thank Dr. Kedar for accepting our request to give us such a wonderful lecture, technical lecture. This lecture connects the theoretical and practical geotechnical engineering. Your profound expertise and insightful knowledge have greatly enriched our knowledge in the field of practical geotechnical engineering by different case studies. I'd like to thank Professor Kaustav Chatterjee, Professor Mahendra Singh, and Professor Samadhya, sir, for the constant support. Today we got a wonderful response from our participants. I can see more than 130 participants joined today. I would like to thank all the participants for making this online lecture successful. At the last, I also like to thank Dr. Kedar sir for accepting our request. Thank you, sir.
Thank you very much.
Thank you, sir.
I think Singh sir is present here. I request Singh sir to speak few words about the lecture.
Thank you, Dr. Birid. It was very nice presentation with case studies, and our students and the audience had a great opportunity, and they had the opportunity to interact with you. So thank you very much for giving your valuable time, and my compliments to my students chapter. They are doing a wonderful job. The participants at the moment is 102. I would like if you could locate the locations also. Can you put it on the map and prepare a small report to keep in record from where the various participants have attended this lecture? So
Yes.
all the best to my students, and thank you very much, Dr. Birid.
Thank you.
Thank
Thank
you
you,
very
sir. Thank you. My pleasure.
I would like for all the participants to open their videos so that we can capture a photo. Kedar sir, you can stop your sharing.
Okay.
Dr. Kedar, you can switch on your video also.
Yeah. I think let me. Is that okay now?
Yes, sir.
Yes, sir.
I think it done, sir. Thank you, sir.
Thank you, everybody. And
Thank you,
bye.
everybody,
Thank you, sir.
for joining today.
Bye. Bye.
Thank you very much, everyone.